Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 1.9 from your textbook, which was our investigation into exact first-order differential equations. In this video, we're going to talk a little bit about how you can convert certain types of differential equations that are not initially exact into exact differential equations using an integrating factor approach. Now, this is not saying that every differential equation out there can be converted into an exact differential equation. We're just going to be looking at some very special sort of situations. So, we're going to take a look at a couple theorems here. We're going to prove this first theorem that we're going to talk about in just a moment, and then the second one has a very similar proof that we'll sort of omit, and then we'll look at a couple examples here. So, let's suppose you have a differential equation of the form mxy plus nxy y prime equals 0. So the standard format that we analyze exactness from. Now, we know that if you have a differential equation in this form, that if you can show that my is equal to nx, so the partial with respect to y of m is equal to the partial with respect to x of n, then we know that it is exact. What we're going to suppose, though, is that those two things are not quite equal. In other words, that it's not exact. What we're going to suppose, though, is that my minus nx, so my minus nx, which would be equal to 0 if exact, well, we're going to assume that it's not equal to 0, so we're going to consider an expression that involves that my minus nx, and we're going to say that if my minus nx divided by the original n is equal to a function of x alone. So in other words, if the partial with respect to y of m minus the partial with respect to x of n divided by the original n function there is equal to a function of x alone, doesn't matter what the function is, as long as it's a function of the x variable only, then an integrating factor of the form e to the integral f of x dx will make the equation exact. In other words, by multiplying by this on both sides of the equation, you will create a differential equation that is an exact differential equation. So let's go ahead and try to prove this. So to do this, we're going to assume that my minus nx over n equals f of x. So we get to assume that this happens. If this doesn't happen, then this theorem doesn't apply, and we don't really have a good way of turning the equation into an exact one. So we're going to suppose that this is true. Then what we're going to do is we're going to multiply this integrating factor onto this differential equation. So we have e integral f of x dx mxy plus e integral f of x dx nxy y prime equals 0. Now what we need to do is we need to show that this new differential equation with this extra factor in there is exact. So we need to show this is exact. Okay, so let's give some names to this. Let's go ahead and call this section here, which we would normally call M, but of course the M is already used there. So let's call it M. What's a good notation? I guess we could call it, let's just use some different letters. Let's call this P. And then this guy here, which we would normally call N, we can call that Q. What we need to show is, if we want to show that this is exact, what we really need to show is we need to show that the partial with respect to y of that P is equal to the partial with respect to x of this q. If we can show that, then we're showing that this differential equation is now an exact differential equation. So let's go ahead and see if we can do that. So what can we say about the partial with respect to y for this p function? Well, we're differentiating this with respect to y. That's not an issue, because if we're treating x as a constant and y as our variable, this is just a constant. So we'll just differentiate that, and it should be pretty clear that the best we can sort of say about that is we get e integral f of x dx my there, excuse me. So why is that? Well, again, if you're doing the partial with respect to y, you're treating x as a constant. This is a constant. Differentiating this, well, we don't know what this function is, so all we can say is that we get the partial with respect to y of that function. All right, let's see about q. That'll be a little bit more challenging because we're going to be doing it with respect to x, which means we will need to treat this as an actual variable. Since both of these have x, we're going to have to use product rule. So let's go ahead and just write that out before we sort of get into it. So that's going to be e integral f of x dx prime times n. I'm going to stop writing n of xy, just n for now. And then plus, we'll have e integral f of x dx, and then we'll differentiate the n with respect to x. So I guess we can say that that's nx. Okay, now we can investigate this a little bit further. So we're taking the derivative with respect to x of a function of x here. So we're going to have to use sort of a chain rule in here. So we can get that this is going to be equal to, if we differentiate that, well, the derivative of e to anything is just going to be the same thing. So e integral f of x dx. Then we need to do the derivative of the inside, or of the composition, which is the integral f of x dx. Derivative of the integral, well, that's fundamental theorem. That's going to give us f of x. And then, of course, we still have the n, and we still have the e integral f of x dx and x. Okay, this is not super great so far because all of this here is supposed to be equivalent to this, and they don't look very similar yet. But at this point, all we've used is the integrating factor. What we haven't used is the actual assumption, right, that we have this very special relation between these partial derivatives, the original n function, and this f of x. In other words, we get to assume that f of x is of this form. So let's go ahead and plug, and we can zoom out just a little bit for a moment. Let's try to plug this in into there. So what do we get then? Well, we get that this is equal to e to the integral f of x dx. That f of x we're saying is equivalent to my minus nx over n times n plus e integral f of x dx nx. Okay, nice simplification now. We can cancel out those n's, so we get that this is equal to e integral f of x dx, and we get that times my minus nx plus e integral f of x dx nx. Okay, should be pretty clear that if we distribute this on here, then we'll have a negative nx e integral f of x dx, and of course we have a positive, so this will cancel with that, and we'll just be left with this component here, which would give us that this is equal to e integral f of x dx times my. What do we notice about that? Well, after all of that simplification, we get that the partial with respect to x of q is equal to this. That's also what we originally had there. So what this shows us overall is this shows us that p sub y is indeed equal to q sub x. So that means that the equation is now exact. And that's exactly what we wanted to prove. So this basically says that if you have this unique situation that my minus nx over n is just exclusively a function of x, then you can use an integrating factor of this form to make the equation into an exact differential equation. Does that solve it for you? No. All that does is put it into the format of being an exact differential equation, which we then have a method for solving. So once again, this integrating factor technique doesn't solve the differential equation, it just simply puts it into a better format, a format that we're more comfortable with solving. Okay, so before we get into our examples, there's an analogous sort of statement if a very similar expression is a function of y only. So I'm going to state that theorem, we're going to talk briefly about it, but we're not going to go through the full proof because it's very, very similar. All right. So we're going to suppose that you have a differential equation, same format, mxy plus nxy, y prime equals 0. And we're going to suppose that this expression, my minus nx, divided by m now, is a function of y exclusively. So notice that the numerator is the same as what we had in the previous theorem, but the denominator is now the original m function. If that's a function of y exclusively, then we can use an integrating factor of the form e to the integral negative g of y dy. So we use a negative sign there, and that'll make the equation exact. The proof is identically analogous to the previous theorem. You just sort of use this assumption, you multiply this type of integrating factor on both sides, you check that the new p and q functions will have those mixed partials that are equivalent, and you're all good from there. So if you want, you can try to prove this in an analogous way to what we just did, just for some extra practice there. Okay, so let's go ahead and take a look at some examples now of this. So we're going to first begin with this. We're going to try to find all solutions to this differential equation. So first thing, of course, is that if we looked at this, we wouldn't be particularly thrilled about trying to use other methods, right? Things like separable is going to be tough because there's so many different terms and it's going to be hard to factor them. Linear, not going to be good because it's non-linear. We've got that like y squared in the denominator. Things like homogeneous of degree 0, probably not, because we don't see everything being a polynomial of the same degree. I mean, we've got degree 2 and degree 2, but then this thing and this thing, those aren't even polynomial terms. Those are rational. It's going to be very hard to phrase everything in terms of y over x. Bernoulli, probably not again, because we're seeing that there's a y, but there's also a y to the minus 1 and a y to the minus 2. So there's several different exponents of y. Bernoulli's probably out. Let's try this exact approach. So let's begin by putting it into the format that we want, which sort of means that we have to factor out that y prime. So we get 3xy minus 2 over y. And if it helps, I'd put some parentheses there. And then let's go ahead and call this. You know what? We also, since we know that at some point we're going to have to start doing derivatives, let's just go ahead and call this 2y to the minus 1, since negative exponents are going to make that easier. And then let's call this x squared plus xy to the negative 2. Y prime equals 0. Okay, in our traditional sort of language, this here would be considered our m, and this here would be considered our n. Now, at this point, obviously in a random problem, we have no idea if it is going to be exact or not, so we need to do our check for exactness. So let's do our check for exactness. So we'd have to take our my. Let's go ahead and calculate the partial with respect to y here. If we do that, looks like we should get 3x, and then looks like plus 2y to the negative 2. So there we go. And then let's go ahead and do our nx, so our derivative with respect to x of this guy. Looks like we're going to get 2x plus y to the negative 2. Okay, these clearly are not equal to one another, so this is not exact in its current format. So we just learned about how to sort of maybe make it exact, though. So even though it's not exact, it's not the worst thing. So let's go ahead and take a look at that difference. So let's go ahead and take a look at my minus nx. So let's take this and subtract this. Should be pretty clear that that's going to come out as x plus y to the minus 2. Okay, now, if we can show that this divided by n is a function of x only, that would be good. Or if we can show that this divided by m is a function of y only, that would be good. So if we look back, right, it seems like this guy is more similar to this, so let's try dividing this by n and seeing what we're getting. Again, this is just sort of some trial and error here. So if we do my minus nx over the original n, we'd have x plus y to the minus 2 over x squared plus xy to the minus 2. Notice that with a little bit of factoring, we get x times x plus y to the minus 2. Okay, that's great. Cancel those, and we get 1 over x. And notice this function of x only. That's exactly what we wanted. If you want, you can try doing my minus nx over m, and you'll sort of get stuck. You won't be able to reduce it to a function of y only, so that would be the incorrect approach in this one. In this case, we want to look at this sort of expression, show that it's a function of x only. Is this our integrating factor? Well, not quite. That means that the integrating factor is supposed to be of the form e to the integral 1 over x dx, which means that it's supposed to be e to the ln x, which we know simplifies to just x. So an integrating factor that will make this exact is a multiplication by x. So let's go ahead and do that. So we're going to take our original differential equation and multiply by x. So we're going to multiply by x. So if we do that on this term, it looks like we should get, you know what, we'll just bring that down so we can sort of see it, make that a little bit easier. You know, we can just rewrite it. We multiply by x. That's 3x squared y minus 2xy to the negative 1. Yep. And then plus, multiplying this guy by x cubed plus x squared y to the minus 2, y prime equals 0. Okay, that's multiplying everything by x. Now, we're going to grab our new differential equation, and we'll finish this up on the next page here. Okay. So let's just give ourselves our sort of problem so we remember what we're working with. So now we have this, which you will notice is just this differential equation multiplied by x and sort of rewritten into the form that we're used to. Now, do we really need to do a check for exactness? No, right? We know that this integrating factor approach is always going to work. That's why we prove the theorem. But just because it's our first example, I will do another check for exactness. So let's do a check for exactness here. I'm just going to put in notation here. This is not necessary. We know that it'll be exact now, provided we didn't make any sort of algebraic mistakes. But, you know, it's not a bad idea to go ahead. So this is now our new m, and this is now our new n. And we can see that my is going to be 3x squared plus 2xy to the minus 2. And our nx here is going to be 3x squared plus 2xy to the minus 2. And notice that now it is exact. So our integrating factor really did work. Again, you guys don't need to do this second check for exactness, but if you want to, it does confirm that you did correctly find the right integrating factor and you did multiply everything out correctly. So there is some advantage to doing this quick check just to make sure everything worked out. You know that it will, provided that there's no sort of algebraic mistakes, but it doesn't hurt to just sort of double check. Okay, now that we know that it's exact, remember what that means. That means that there exists that phi of xy such that the phi x is equal to that m, and the partial with respect to y of phi is equal to n. So again, doesn't matter which one we sort of choose. We can start with either one. I think in the previous video, we always started with this. So just for fun, let's go ahead and start with this one this time, just to show the different ways of approaching it. So we're going to start with this. Again, we can choose either one. So what does that actually tell us? Well, that tells us that the partial with respect to y of phi is equal to that n, which is x cubed plus x squared y to the minus 2. So we're going to go ahead and then say that phi is equal to the integral of x cubed plus x squared y to the minus 2. And we're going to integrate dy because we chose to do it like that. This is a constant with respect to y, so integrating a constant just gives us our variable. So we get x cubed y. Integrating this, we're going to get that negative 1 exponent and then divide by that. So negative x squared y to the minus 1. And then we would get an unknown constant, but again, since we're working with respect to y, our unknown constant is really thought about as a function of x. So we'll say h of x. So there's our phi function. We know that this is the sort of multivariate component, and there could be a sort of unknown function of x associated with it. So now we can go ahead and now use that phi sub x equals m. So let's go ahead and do that sort of over here. Okay. So phi sub x equals m. What does that actually tell us? Well, we differentiate this with respect to x. Looks like we get 3x squared y minus 2xy to the minus 1 plus h prime is supposed to be equal to this m component. M was this thing right here. So looks like we get 3x squared y minus 2xy to the minus 1. So notice that all the multivariate stuff is going to cancel out, and we're going to get h prime of x is equal to 0. So technically h of x is equal to a constant, so unnecessary, right? We don't actually need to include that because it's not really a function of x, it's just an unknown constant. So this tells us that phi of xy is actually x cubed y minus x squared y to the minus 1. And that tells us that our general solution overall is x cubed y minus x squared y to the minus 1 equals some unknown constant. So there we got our general solution to a non-exact differential equation where we chose an appropriate integrating factor and then use that to make the equation exact. Okay, let's go ahead and take a look at one more example of this. So we're going to try to find all solutions to this differential equation. Once again, the first thing that we're going to sort of need to do is we're going to need to rewrite this into this sort of format where we test for exactness. So we're going to need to subtract this over onto the other side. So that's going to give us cosine xy, y squared, plus exy, plus, and since I'm going to subtract this over, I guess I can just negate the inside here. So cosine xy times xy minus y prime equals 0. Okay, so there's our differential equation. Again, other techniques, things like separable, it's going to be very hard to separate the things inside the cosine xy. Linear, you have functions, cosine in this case being applied to y, so that rules out linear. Homogeneous, degree 0, same thing. I mean, how are you going to get a cosine of y over x when you have cosine x times y? Not going to work out very nicely there. And Bernoulli is also out because, again, the nonlinear component isn't coming from y to an exponent, it's coming from a function applied to y. So our previous techniques are sort of out there. So we can use a little set of parentheses to sort of keep ourselves a little bit more organized there. This whole component is going to be our original sort of m there. And this whole component here is going to be our original n. So let's do our check for exactness. Notice that you always want to do this initial check for exactness because if it is initially exact, well, great, you can just solve it then. And if it's not, you still need to know about the original my and nx to help deduce what the integrating factor should be. So our my here is going to be a little bit messy. We've got to differentiate this with respect to y. This in here is going to be initially a product rule. So the derivative of that cosine is going to be negative sine of xy. Derivative of the inside with respect to y is going to be x, and then y squared. And then we differentiate the y squared, so we're going to get 2 cosine xy, and then y. And then we differentiate the last component and just get an e to the x there. So there's our my. And let's look at our nx. So our nx, same thing, going to be a product rule here initially. So differentiate the cosine, we're going to get negative sine xy. Differentiating the inside, we get a factor of y, so we get xy squared. Then we'll go ahead and differentiate the x, so that's just going to drop out. So we get plus cosine xy y. And then we differentiate the negative y at the end, but since we're differentiating with respect to x, that's going to drop out. So there we go. Pretty clear that these two things are not equal to each other. Yeah, these are not equal. So it is not exact right now, as expected, because that's what we're trying to work on here. Okay, so let's measure in some ways how non-exact it actually is. So we want to go ahead and do my minus nx, nice sort of Christmassy colors there, right? Let's go ahead and actually see how sort of off these are. So we're going to subtract this by this. And if we do that, it should be pretty clear that we're going to end up canceling these, and then we should get cosine xy plus e to the x. Because these terms are going to drop out, this subtraction is going to give us this, and then that e to the x doesn't have anything to subtract, so there we go. Now, what we'd like is if this expression here divided by the original divided by the original n up here is equal to a function of x, that would be good. Or if this divided by m is a function of y, that would also be good. Now, if we look back, because I see this e to the x here, I don't really like the idea of trying to divide by this. So let's actually try to divide by m, and hopefully we can cancel some of those things out. So let's go ahead and take a look. We're going to try to look at my minus nx over m. So that would be cosine xy plus e to the x divided by, and then we're going to divide by this original m. So it looks like that would be cosine xy plus e to the xy. Doesn't initially look good, but notice that with a little bit of clever factoring, we can see this as cosine xy plus e to the x over y times cosine xy plus e to the x. Did I make a mistake there? Oh, yeah, this is a y squared down here. Sorry. It looked a little funny. Yeah, this is a y squared initially from our m. Sorry about that. Just sort of a miscopy. And then once we factor that out, I'll need to rewrite that denominator. Once we factor out that y, we get cosine xy plus e to the x. These things are the same, so we can cancel those. And it looks like we get 1 over y. This right here is a function of y only, which is exactly what we wanted, because we did my minus nx divided by m. It had to come out as a function of y only so that we can actually use our integrating factor. How do we determine the integrating factor? Well, the integrating factor should be e to the integral. Since we found a function of y, we need to negate, so negative 1 over y dy. That's what that second theorem that we didn't prove said, but it would have a very similar proof. That would be e to the negative ln y. Standard trick here, put that as an exponent and then cancel. Looks like our integrating factor is y to the minus 1, which is 1 over y. So sort of a unique coincidence here. This guy actually is the same, but that, of course, is just pure coincidence. We really always have to do that e to the integral of whatever we find here. So our integrating factor is 1 over y in this case. Let's go on to the next page and actually use this to figure out how to solve this differential equation. So I'll use this so that we can see the original differential equation. Remember, we had rewritten it into this format. Plus cosine xy minus y prime equals 0. We just figured out that the integrating factor is supposed to be 1 over y. So in other words, we're going to divide everything by y. So let's go ahead and do that. We get cosine xy plus e to the x plus cosine xy minus 1 y prime equals 0. Now, of course, by multiplying by 1 over y, you're really dividing by y. So we should make the little assumption here that y is not equal to 0, and we will need to probably go back and check that at the end. So let's go ahead, though, and proceed from here. All right, again, we don't need necessarily to do another check for exactness, but we might as well. So let's do our check for exactness. So again, this is now our new m, and this right here is our new n. So our my, so differentiating this with respect to y, looks like we're going to get negative sine xy. Derivative of the inside is going to be x, so we get xy. And then we have to continue doing product rule, so we get plus cosine xy. Then, of course, this part just drops out. For nx, well, for nx, we got to differentiate this with respect to x. Looks like we're going to get negative sine xy. Derivative of the inside with respect to x is going to be y. So we get xy. And then finish up the product rule, differentiate the x. It's just going to drop out. So cosine xy. And what do we notice? This is exact now. Of course, because this integrating factor approach always sort of works if we can find it as a function of x or a function of y exclusively. But there we go. Okay, so let's go ahead and finish this up then. So there exists this phi of xy such that the partial with respect to x of phi is equal to m, partial with respect to y of phi is equal to n. So we did y in the last one. This one, let's just choose phi sub x equals m to start. Let's start with that one. So that tells us that phi sub x is supposed to be equal to this m that we have right here, which is cosine xy times y plus e to the x. So to begin solving for phi, we can integrate this with respect to x. A little bit messy to do so, but on this first component, notice that the derivative with respect to x of xy is equal to y. So you can actually do this as a substitution. If you want, you can write it out. U equals xy. Du would be y dx. So this is going to be a u substitution there. So we can go ahead and integrate that. Integral of cosine is, of course, sine. So we get sine xy. And then the integral of that e to the x is e to the x. If that's a little unclear about how we did that u substitution with this sort of partial integration, just keep in mind you could check by differentiating this. If you differentiate, you get cosine xy times the derivative of the inside, which, since we're taking a derivative with respect to x, is going to be that y, and then we get back to where we started. And then, of course, we have our unknown function, but it's going to be an unknown function of the other variable, which is y. So now we can use that phi sub y equals n. So to do that, let's go ahead and sort of move ourselves back over here. So phi sub y, let's differentiate this with respect to y. So that's going to be cosine xy times the derivative of the inside with respect to y, which is going to be x, times the derivative of that. That's going to drop out, and then we're going to get h prime of y. And that is supposed to equal our n, which was this thing right here. So this is supposed to equal cosine xyx minus 1. Notice that the multivariate component, this stuff, is going to cancel out on both sides. So we're going to get h prime of y is equal to negative 1. That means h of y is the integral of negative 1 dy, which means h of y is equal to negative y. So this tells us phi of xy is actually equal to sine xy plus e to the x minus y. And if we look at that, that means our sort of solutions here, solutions are of form sine xy plus e to the x minus y equals a constant. You'll notice that I'm being careful about not saying the general solution, because we got to go back and check this thing here. If we do a quick check, y equals 0. Well, let's go back to our original differential equation, y equals 0. If y equals 0, this term will be 0, this term will be 0, this will be 0, this will be 0, and of course y prime will be 0, 0 equals 0. This guy does work. So we get solutions are of this form, and also we get that one extra particular solution, y equals 0. So there we go. It doesn't have a general solution in this form because we've got all this family, and then we also have y equals 0. So there's a couple examples of solving non-exact differential equations by using an integrating factor to make them exact. This basically wraps up our techniques for solving first-order differential equations. This means that for first-order differential equations, you guys should be comfortable working with separable, linear, homogeneous of degree 0, Bernoulli, exact, and exact with integrating factor. Those are our 6 sort of main techniques or main situations that we've covered for first-order differential equations. In our next video, we'll be taking just a quick look at some ways of approximating solutions to differential equations from a completely numeric perspective.